So far we have seen how to execute the instruction, especially we have focused on how to execute the instruction but not how to fetch, right? Now to fetch the instruction we need circuit, correct? That means someone has to modify the program counter, correct? That's why this is a circuit. So this circuit is especially dealing with program counters updation, okay? Now also fetching the instruction. We will see how this circuit is going to help us in fetching the instruction. So before going to the details, first of all, I'll give you a rough outline of this circuit. What this circuit is doing is, forget about this branch offset first of all, okay? So I will teach that later. At this moment, only focus on this line 4. Always assume that this multiplexer is selecting 4. So if you focus on this part, then program example at any time, whenever I perform operation, that means example if I ask the circuit, my dear circuit start functioning, then what is going to happen is this program counter value will be taken here, 4 will be taken here. So program counter plus 4. So program counter is going to get, you see, PC value plus 4, PC plus 4 is traveling like this and it is coming back and it is getting stored in PC. Okay. So this circuit can be designed so that within one clock cycle, assume that let's say we are using only one clock cycle to get the value stabilized. Okay. So within one clock cycle what can happen is program counter can be incremented. Okay. So such a way we can plan within one clock cycle. You don't require much time. Now, sir, what is this PC temp? I will explain that later because it will be good to understand this PC temp with call instruction, okay, with some instruction. I will explain that. Forget about this. If there is no such kind of thing and there is no immediate value, what is going to happen? Simply program counter will be incremented by 4, correct? Apart from that, you see this cable, this blue cable, it is connected to multiplexer. Again at this moment, forget about the another line, okay, this line. Of course this line is coming from that memory address, you know that stuff, right? So whenever you want to access a memory to fetch the operand, to get the operand, so this memory address we use. At this moment, forget about that, okay? In the first clock, I want to say that in the first stage, what is going to happen is your multiplexer selects this line, okay? So in the first stage, program counter's value will be taken like this and memory address that is connected to memory address. That means your multiplexer is sending that to memory address and there is a memory interface, already I explained you, right? So when you send that program counter's address to memory interface, so that memory is going to give us data, which is nothing but instruction, correct? Now we store that in instruction register. For that this is a circuit. There will be instruction register which is connected to memory data. Okay. Now memory interface will work like this. It will ask like this. You give me address, I will send the data to wherever you want. Okay. So such a way we can plan it. Now remember one thing, within one clock cycle we can do all these two stuffs. One is sending the program counter to memory interface. At the same time incrementing the program counter, they will be done simultaneously. One cable is coming like this, correct? So that example program counter value is 100, then 100 is sent to memory interface. At the same time, that means within one clock, that 100 will be immediately updated to 104, right? So 100 is going to memory interface, 104 is going back to program counter. In that way, so two things will happen in one clock cycle. Okay, such a way we can design a circuit, not a problem. Now we will see the clear idea like what is going to happen. Okay, this is a rough idea. Now we'll see with the instruction. Let me take one instruction and let me explain you how this circuit is going to work and what area, otherwise which components are going to be active at any time we will see. Let us take load R5 X of R7. Okay. Now we know that X is nothing but immediate value. Now R7 is one register, R5 is another register. In the first stage what should happen I will tell you. These are the operations I am expecting. My circuit supports it, don't worry. I will show you how to take the support from the circuit. Why circuit will do that stuff? Because such a way we designed it. First of all, what is my expectation? You see, first thing is the program counter's content should be sent to memory address. Okay, so memory address is nothing but it's a register, I can say. Okay, assume that it's a register. When you send the data in program counter to memory address register, okay, usually in some of the textbook they say that is memory address register. We can say memory address register. So send program counter's value to memory address register. Now since memory address register is connected to that memory interface, automatically that memory interface will give you the data which is located at memory address register. Okay. Now see, what are the operations I am expecting in stage number 1 is send program counters value to memory address, that means memory address register. So that interface will start working and it will read the memory. So read memory means that interface, memory interface is going to work for us and it is going to give us data. Sir, we have a doubt here. What is that? Within one clock cycle, can we do all this stuff? That means can we read the memory also? Generally, it is not possible. I will tell you the reason. How your memory is organized, you will be studying that in very detail. At this moment, you see rough idea. So your memory is actually, divided into two parts, cache memory and main memory, correct? Let's take primary memory, main memory and cache. Generally cache is very fast, so that within one clock cycle, when you provide the program counters value, then within one clock cycle it can fetch, it can give you the data back. Okay, that means your instruction register can be filled with the data which is stored in the cache. One clock cycle is enough. Understand? But sometimes you may not get the data in cache. You will be studying that. So that is, I will give you the one analogy example. Let's say, so you are taking the I can say household items, like example, let's say every day you purchase some of the household items, right? Like coffee powder, otherwise milk, everything. Do you get everything in your nearby shop? Maybe in the corner there will be, let's say there is a shop, and every day you are purchasing some of the items from that shop. If you want milk or coffee powder, anything, do you think always you get there? No. But if you get there, then within 1-2 minutes you can get whatever you want. Sometimes what happens, some of the items which you want might not be available in that shop. Then what to do? You will go to main road. If let's say in main road, if that shop also doesn't have the items which you want, then you will go to supermarket, which is, let's say, 3-4 kilometers from your house, right? That means what? Getting the items for your house, for your regular day to day activities, might not be possible in 5 minutes or 10 minutes. Sometimes it takes only 5 minutes, sometimes it takes 10 minutes, sometimes one hour, sometimes one day. Example, sir, example, let's say you want to purchase one hi-fi, I can say Apple phone or something. So you might require 1 or 2 days, correct? You have to order it. You might not get that in your city. Then we have to go to online, and we have to, but I mean, you have to book it, and within maybe 2-3 days it might take, right? So finally, here also same thing. Memory access may not be constant time thing. So sometimes it takes 1 hour, sometimes it takes 2 hours. In that way, here also sometimes it takes only 1 nanosecond. That means, let's say, one clock. Let us talk in clock terminology. Sometimes it may take one clock cycle, sometimes it may take 5 clock cycles. It depends on the availability of the data, correct? So that's why at this moment we don't bother about it. We will see how to deal that stuff later. At this moment, assume that always your data is in cache. So when you provide the data, I mean address, within one clock cycle, you are getting the data back in instruction register. That is what I wrote. Now see, first step, program counters data address should be provided to that memory interface. Then that interface will read the memory, then you get the memory data back. That memory data will be transferred to instruction register. After instruction register is a register, right? So once you get the data in cache, example it is here, then we have to transfer that to instruction register like this. It takes again very less time. Within one clock cycle we can plan it, not a problem. It's not a big deal, because cache is very small memory. Now after that, see, this program counter incrementation is not depending on all this stuff, right? This program counter is, this adder is not waiting for memory access, memory interface, right? So that's why program counter will be immediately incremented. It will take very less time. So since we are doing some of the things parallelly, example like program counter incrementation, correct? Only these three are related, but we can do them in one clock cycle. Overall, this entire thing, stage number 1's activities we can do in one clock cycle. Okay. Now we'll see the second step. In the second step, what we do is, already our instruction register is having the data, right? I mean instruction. So we have to decode it. For decode, sir, what is the meaning of decoding the instruction? There is a control circuit. Sir, you did not teach us? Yes, I will teach that. That is the heart of the entire story. So how to design that control circuit, we will see. That control circuit is going to, decode the instruction, and it is going to understand what is the meaning of that instruction. Is it add, is it subtraction, is it multiplication, is it, apart from that, that instruction is direct, immediate mode addressing mode, otherwise direct addressing mode or indirect addressing mode. Everything will be understood by your control circuit, and appropriately it is going to take the operations. So the remaining operations will depend on the decode instruction. Let's say properly that instruction is decoded and your processor understands what's the meaning of that, then it realizes that it is a load instruction. Now by this time your processor understood that it is a load instruction, and register 5, register 7 and X, everything is specified, their addresses are specified in the instruction. So in the second level, what is going to happen, you know that, right? So we send R7 value, content of R7 to RA. Okay, if you want to see that, I will show that in picture. So we have to send content of R7 here, you see R7, right? So here we have to send R7 here, so that will, if you give this input line to R7, then automatically that content of R7 will come to RA. That is what I want to tell you here. Okay, yes. So done. We can, it's not a big deal, right? So within one clock cycle we can do it generally. Now in the third clock cycle we will do the stage 3 work. What is the stage 3 work? Recall. So finally R7 is connected to that input line, correct? Now we have immediate value X, recall. Assume that X is something 100. Then in the third step, what we are going to do is RZ equal to RA plus immediate value. This immediate value should be connected here. See, here we connect here immediate value. And what is the second thing? RA already, see, in the second stage, RA getting the data from R7, correct? Now RA already having R7 value. That R7 is, and this immediate value are connected to ALU. In the third step, what is going to happen? Addition will take care. Addition will takes place, right? If addition takes place, so what will be added? RA. Second one, this, assume that this multiplexer is, properly selected so that this immediate value is coming here. Then X plus R7 will be done here, right? So here in the third step, RA value, which is nothing but R7 value plus immediate value X plus RA. Now in the fourth step, what we have to do? Recall what is the meaning of load. This X, now effective address has been calculated, X plus R7, right? So that X plus R7 is calculated here, getting calculated. After that, this one, fourth step. So the fourth step is what? Memory address equal to RZ. Recall. What is RZ? I just to show with the picture. RZ. See. Now already by this time, when you are executing the fourth stage, already third stage is done. Then the data in ALU out is what? You know that, right? This is X plus R7. That X plus R7 is sent to memory address. That is what you see. Send that RZ value. See here, RZ value is nothing but X plus R7. Send it to memory address. Now already you know about memory address. Whenever you send X plus R7 to this memory address here, what is going to happen? That interface will start working and it will give you the data back, right? Now, so see here, we read the memory which is given to memory address. Now that memory data we are storing back to RY. See that memory data comes, right? That we store in RY. Already I explained you, right? For that properly this multiplexer should be selected. Understand? So here only one question you should have, sir. Why this line is selected? Why this line is selected? When this line will be selected? That will be taken care by control circuit. Don't worry, I will see that. That is what the main thing here. So RY will be in the next level, you see. Now the fifth step, forget about that. You see here, already when you have data here in the load instruction and you want to store the data into R5, correct? So here we will be specifying R5. Already you know the mechanism of the circuit, right? This circuit can take two inputs, right? Sorry, two outputs and one input, right? So if you connect here R5, then there will be one register called R5 in the registers that will be enabled. Then this data, where whatever you are sending RY, that RY value will be transferred to R5 in the fifth stage, correct? So since already you know in the fourth stage we have computed this ry value, right, in the fourth stage. So memory data is transferred to ry. Now I'll ask one question. After end of the fourth stage, what is the content of ry? Definitely the data which is loaded, right? That means the data which is stored, which is located in X plus R7, correct? Now that where we have to store in R5. So if you simply, what we have to do, already there is a cable, you see, data automatically will be transferred. Simply we have to enable this register. So that's it. It's not a big deal, right? Automatically this data will go to R5 in the next cycle, correct? So in that way, so this circuitry is perfectly working and it will execute load R5 X of R7, correct? Now these are the instructions. You read that instructions and try to, locate that positions and try to understand it on your own also. Okay, stop the video and see all these instructions once, and you see, the data flow. Okay, now we will see how this circuit can be used to execute store instruction. Okay, now we'll see store instruction. So how to execute store instruction, we'll see. How the circuit supports, we will see. First step is common, you see, because we are not at all fetching the instruction. Without fetching the instruction, we can't do anything different, right? So that's why first step is again taking the address from program counter, right? First thing is send the data in the register program counter to memory access register, right? So the memory address register. So again assume that there is a memory address register. You might assume like that, but that is not compulsory. So it's a implementation dependent. So assume that, let's say there is a memory address register, you are sending program counter's address to that memory address register here. Once you send it, automatically that memory interface will start working and it will give the data. Already I explained that, right? So this step is pretty clear. Stage 1 is pretty clear, correct? In the stage number 1, program counter address will come here. So memory will start working and it will give the data back to instruction register in 1 clock cycle. So program counter will be automatically parallelly incremented. So once clock cycle is done, in the second clock cycle, what is going to happen? Sir, why in the second clock cycle only that machine will start working? That means that circuit. So it's not like that. Everything will be ready, but which circuit you enable is important. Okay. So when are you taking the data is important. Now what we do is, in the second step, we will be decoding this instruction, and after that we connect this RA. See, by understanding the instruction type, what we are going to do is, we are going to connect R6 to RB, RA to RA. Okay, so we know that, right? This is A, this is address A, this is address B. So here you give RA, here you give, sorry, this is not RA. Here for A, if you see here, for A we are giving what? R8, for B we are giving R6. For A you give R8, for B you give R6. If you do that, what is going to happen? See, so here in the second step, R8's data will come to RA, R6 data will come to RB. Yes, right, in the second stage. So this circuit should start working. Okay, it might work in the first cycle also, but we are not interested at that time seeing that, correct? In the second clock cycle, if you observe the data, then definitely that RA and RB contains what? Sir, what about in the third stage? What happens in the third stage? Anything can happen. In the third stage also, that RA and RB might show same data, but we are interested in second stage or in the second clock cycle. In the second clock cycle, if you see RA and RB, definitely they contain what? This data, because in the first clock cycle we are understanding, we are connecting the, so in the second clock cycle we are connecting R8 here and R6 here. So within one clock cycle, so you get RA and RB contains R8 and R6. I can say that here R8, here R6. That might take at most one clock cycle. So within two clock cycles, finally, so RA and RB got the values which are desired. Okay. Now we'll see the third step. In the third step, that means in the third clock, actually stage 3 generally we do in the third clock cycle. In the third clock cycle, I am expecting this one. What is that? RZ equal to RA. See, that means RA's data we have to send to RZ. That RA's value to be added to immediate value X. Yes, we can do that, correct? How to do that? you connect this immediate value field, this cable to X. Okay, now already X is available in the instruction. Then instruction register is already carrying this instruction, right? Store R6 X of R8. What you do is this portion of the memory bits you connect to here, so that X will be taken here, R8 will be taken here, then X plus R8 will be done automatically, correct? So and that data will be ALU out is flowing, the value is flowing to RZ. So can I say one thing, if you give one clock cycle of time, within one clock cycle of time RZ is going to get what? X plus R8, yes or no? Yes, that is what here it is mentioned, RZ equal to RA plus immediate value of X, which is RA's content. Already I told you that it is R8, that's why X plus R8, not a big deal. Now RM should get RB's value. So RM, already I explained this part, right? When I already explained you store instruction, you just go through that. See, since you connected RB to this RM, so if you give one clock cycle of time, if at end of the second clock cycle data R6 is available here. If you give one more clock cycle of time, because we are talking about third clock cycle, in the third clock cycle this RB's data will flow like this and it will settle in the RM register. That's why RM contains now RB. That is nothing but, I think, R6, correct? It is R6, remember it. Now finally RM contains R6. Here let me write R6. Now fourth clock cycle. Now in the fourth clock cycle slowly data flow like this, that's why it is called data path. So data, this register's values will flow like this. Now this multiplexer will start working, but which control line, otherwise which selection line is enabled, we don't know, right? But it depends on the instruction. Since it is store instruction, what we have to do, we should not enable this, we should not bother about this one. We have to take the data from here, we know that, right? This memory address. So in the fourth cycle, that memory address should be specified to read the memory. See, so memory address which is coming from RZ, that should be sent to that memory address register again, correct? So my dear memory interface, RZ contains some data. What is that RZ data? X plus R8. X plus R8. That will be given to that memory interface and the corresponding data comes to, see, the memory data comes to RM, right? That means, sorry, RM, because it's a store instruction, so we have provided address and we are providing the data, right? Mr. RM contains the data which is to be stored. Now we are giving both of them and simply write memory, correct? So because of this write memory operation, what happens, that interface will take the data RM and the address which is in RZ and it will store into appropriate location. In the fifth step, what we have to do? Nothing. That means, sir, this data will go back, right? Yes, but we have not taken any selection line, right? Because this is not selected, so in the next step nothing will happen. So data will not go back to register file. In that way you can understand, right? So this is about executing the store instruction using this circuit, correct? So what is my goal? Sir, why are you teaching all this stuff? You are almost have taken a complete picture of a computer, a small computer, and you are executing all the instructions. What is the purpose? If you know what is happening really when you are executing the instructions, okay, then any gate question you can solve related to ALU and data path, because suddenly they ask questions related to this kind of circuits. And concept is very simple, you can easily understand, but you need a practice. That means before going to the exam hall, you should have a practice of solving this kind of big circuits and understanding the flow through big circuits. That's why I'm taking big circuits and I'm explaining you. But don't expect direct question from this kind of models, but automatically you can solve gate questions which are related to this kind of models. So there are a lot of such questions. They simply give a data path and they ask some questions related to outputs, like what will be the output, what is the content of that register after 2 clock cycles or 3 clock cycles. They will not be very big deal for you if you understand this concept. That's why what you do is simply attend the lecture and understand whatever I'm teaching. That's it. Forget about everything. So you can your prospects will be improved and you can solve all the gate questions related to hardwired programming, hardwired and micro programming. Okay, don't worry. Now I will take the next instruction this time, that is branch instruction. Okay, now we'll see branch instruction. let's say branch of 200. I am assuming that relative addressing mode. So in the relative addressing mode, what happens when you write branch of 200? So 200 is not an absolute memory address where we are going to branch. We are jumping to 200 plus the current program counter. Such a way, so we are going to do the things. We will see that. So first step, quite common. Take the program counter's value and fetch the instruction. And now currently, once this step is done, now this instruction register contains that branch instruction, right? Branch 200. Now after that, second step is obviously decoding. So after decoding, your processor understands that it is a branch instruction. So properly that inputs will be connected. How that inputs and outputs will be connected, I will tell you. Nothing to connect here because we don't have any registers to connect, right? Directly we gave you absolute value. So that 200 we will be giving here, see, branch offset. That branch, so your processor understands that it's a branch instruction, and in the second stage it is going to connect this cable to 200. Now here there is, see here, nothing here, okay, we don't give anything here, so that though whatever the previous values, in the previous values might be anything and anything can flow like this, doesn't matter, we are not considering them, correct? That's why don't worry about that. Now what is going to happen in the third step, we'll see. Program counter, this circuit will start working. Of course every circuit will start working every time, but at this moment we will be taking, otherwise we are focusing on this part. Really, if you, in the third clock cycle, if you see the data, what happens is already program counter contains some value, right? Whatever it is, that program counter's value plus branch offset. Already program counter is incremented by 4, correct? So example, let's say whatever it is, doesn't matter. Now program counter's value, old value plus branch offset. So branch offset is here. For that, properly this multiplexer should be enabled. This time 4 should not be added, but this one should be added, right? So this time 200 will be selected. So adder again will start working. So this time 200 maybe, so 200 here plus this current program counter value will be added. So program counter will be updated properly, right? So this time what happens? Example, currently your program counter is showing 104. 104 plus 200, 304. So program counter will be updated to 304. You remember it. In the next step, nothing, keep quiet. In the fifth step, nothing, keep quiet. So if you do that, what is going to happen? Only this program counter will be updated because of the instruction, and it will show 304. Next time, if you fetch an instruction, which will be fetched? Instruction at 304. That is what the meaning of jump instruction, correct? In that way, branch can be executed. So the execution of branch is nothing but updating the program counter, and we can do it. The only thing is this multiplexer should be selected properly. Now what I want to tell you is these circuits are really working properly to execute any instruction, but only thing is appropriate multiplexer should be, that means appropriate selection line should be selected by the multiplexer. That is what I would like to say. Now we will close this idea by understanding the last model, that is call instruction. Let me explain you call instruction, okay? Now we'll see call instruction, okay? So here call is, the model of instruction is like this. Let's say call R9. R9 contains the function address. Example, let's say you have a function. That function, let me show main memory here. This is your main memory, and that main memory contains one function, okay? That function is located here. Instructions of that function here. And assume that this address is 500, okay? Now we have to go to that 500 to execute that function, but what I'm doing is rather than directly giving call 500, we are giving that through register, okay? So assume that, let's say R9 is a register which contains a value called 500. Now whenever I say call R9, if this instruction is executed, then control should go to 500. That means program counter should be updated with 500, so that next time instructions will be executed from memory location 500. That's it, okay? You know the idea. And what is the main concept of call instruction? Whenever you execute call instruction, the control should go, example, let's say control is at 100, okay? Currently your program counter is showing 100, let's say. Then we have to jump to 500 because of this instruction execution. And one more thing, we have to remember the return address, correct? So finally, because of this instruction execution, return address should be stored. Assume that, let's say, so your CPU registers contains one dedicated register called register link. Okay, so what we have to do is we have to come back once this function execution is done. We have to come back to program counter plus 4, correct? That means we have to come to 104. You know that, right? Because you are executing at 100. The next instruction supposed to be executed is 104, but because of this function call we are going to some other place and we have to come back to 104. This is what my expectation. Now you see why this circuit is going to execute this call instruction. We will see. First step, as usual, memory address whatever the data is in program counter that you execute, correct? So that you know, first of all, this instruction will be fetched, correct? Assume that, let's say, this is the instruction at current program counter address. Okay, now automatically this instruction register gets that call instruction. Okay, call R9. Now second line, so program counter will be incremented. So program counter will be incremented, and because of this one it will become 104. You know that, right? So when first line is executed, program counter will be, because this adder will work, we know that everything. So program counter will become 104 because of these three steps. Now I am not discussing these steps. We'll directly go to stage 2. In the stage 2, decoding will be done and we understand that it is call instruction. Then we connect R9, you see, to RA input. So your control circuit will connect this input line, output line to R9. So because of that, the data in the register R9 will pass through like this. Okay, now after second clock cycle, RA contains R9. That means value of RA is R9 value. Remember it. Now third clock cycle or third stage. In the third stage, what is going to happen is, see, RY equal to program PC temp. So we are going to use this register. Now let me focus on this register. I did not explain this, right? I will tell you what is this. Simple. In the first clock cycle, you incremented program counter, right? In the second clock cycle, what happens? See, first that 104 will slowly, in the next clock cycle, it will slowly will come here, and you know, it will be settled here. What I want to tell you is, at the end of the second clock cycle, this program counter temp is 104. Remember it, correct? Now, so that is connected to return address. Remember it. So that is connected to return address. That's why, so this one program counter temp, I can say, is connected to this return address. So remember that. Okay. Now simply the program counter's value will be stored in program counter temp. Yes. So that is 104. That you remember. In the third stage, what is the other thing we are doing is, so program counter is loaded with RA. So what is RA, sir? Recall this RA. What is that RA? In the second clock cycle, end of the second clock cycle, RA's content is R9. So slowly that R9 will come and it will settle in program counter. Remember it, program counter gets R9 here in the third clock cycle, and PC temp will take old data of program counter, which is 104. Just remember it. Okay, so this is very important step. Let me revise it. In the second clock cycle or in the second stage of execution, instruction will be decoded, so that this, in the second clock cycle, R9 will be connected here. At the end of the second clock cycle, that R9's data will slowly will come here, and now this buffers. That's why this stage buffers are very important. So after second clock cycle or after second stage, these buffers contain what? RB, I don't know, because I did not mention anything for B, but RA contains R9 after end of the second clock cycle. After third, in the third clock cycle, what is going to happen is, assume that though I did not mention, this RA is connected here. This RA same. Okay. Now here you see. Otherwise, let me show like this. Actually, it is connected like this. Now, at third clock cycle, what is going to happen? Since RA contains R9, at the beginning of the third clock cycle to end of the clock cycle, slowly R9 will flow like this. Assume that this multiplexer is, selecting this cable. That is what my assumption. Okay. Such a way we can plan it. That is what the job of control circuit. Then what is going to happen? Especially for this instruction, we should select this line, not this line. So that what is going to happen? You see, R9 will flow like this. At the same, when will it happen? In the third clock cycle, correct? So in the third clock cycle, if the data R9 comes to program counter, then the old data is bypassed here, you see. At the same time, the old data will go to PC temp. That's why in the third clock cycle, if I write, that means what is going to happen because of the circuit is PC value is stored in PC temp. Yes, PC value is stored in PC temp. At the same time, data is coming from here to here. RA value is stored in PC. That means PC contains R9. That's why now PC contains R9. You remember, and PC temp contains 104. Old PC value. Correct. Now after that, fourth clock cycle. In the fourth clock cycle, what is going to happen is, since this PC temp is connected to multiplexer Y, that means see, already I told you that there is a return address, right? This return address is nothing but this cable. Okay. Now in the fourth clock cycle, this fresh data slowly will come here. Every time it comes like that, but your multiplexer this time will be properly selected so that this line will be selected. Really, if this line is selected, what is going to happen? You tell me. In the fifth clock cycle, that RY, which is nothing but return address, which is 104, that 104 will be C. I am talking about fifth clock cycle, correct? In the fourth clock cycle, what happens? In the fourth clock cycle, we know that this is the fourth stage. In the fourth stage, this multiplexer will be selected and RY will come here. That means, sorry, so this return address will come to RY. So that is fourth clock cycle. In the fifth clock cycle, the same 104 will travel like this and it will go to appropriate register. Which register, sir? Here you did not select anything, right? But automatically, especially for this kind of call instructions, R link register, because who should store the return address? Link register, correct? Already I told you in the addressing modes topic. Assume that, let's say, automatically that R link register is getting selected and that will be transferred here. That means R9 value is transferred here. Sorry, RY. So what is that RY value? 104. Now currently, after execution of this entire instruction, what is R link contains? 104. Such a way this I can say this device is designed. Okay, that is enough. So in that way we can happily execute call instruction. Okay. Now if you have any questions, don't worry, just go through it, like how the circuit is working. Understand? Now finally this small circuit is executing load instruction, store instruction, call instruction, everything, correct? But we have to select the proper control lines. That means, you know, this multiplexer example, sorry, this multiplexer should be properly selected, whether this line or this line, here this line or this line. In that way everything should be properly selected. That will be done by control signals. So now so far we have not understood what is control circuit and how to design it, right? Now we will see that part. Up to now what happened, I will tell you. You understood how a typical circuit looks like, correct? How a processor looks like and how data path looks like, everything you have seen, correct? Now we have to see how these multiplexers and, you know, the remaining things will be properly selected and enabled so that at right time right things will happen, right? So that we will be seeing, that is nothing but designing of control circuit. Okay.